In this video we're going to talk about root finding, which is a technique for, despite what the picture says here, it's a technique for solving for where a particular function is zero, which is helpful to solve many different kinds of equations. One application in biomedical engineering has to do with figuring out the right calcium levels so that muscles contract at the right rate, with the right force. As we all know, calcium has a fundamental role in the propagation of electric activity that accompanies muscle contraction. You can see typical calcium waves here precede, accompany the electric signal and precede muscle contraction, and it's part of a complicated pipeline of transport of molecules throughout the cell. Here we have a video of actually this video. The intensity here is proportional to the amount of electrical activity in this group of cells, but you can see that they are beating in rhythm. These are cardiac cells, but at a certain point we have too much calcium in the system, and you can see that they are not beating in synchronous rhythm anymore, and then arrhythmia can happen. It just so happens that there are genetic therapies that can be used to, let's essentially regulate the amount of calcium that is present, or that is just enough so you can have normal heart activity. But figuring out the exact level for these calcium buffers, so that you can have the right amount of free calcium. There's total calcium, there's free calcium in your system, is not a trivial matter, and it requires us to solve for the buffer levels that give you the right calcium level, right? So let's say if you have knowledge of a total calcium on the left hand side, and you have knowledge of the reaction rate constants as well as the concentration of the different buffers, what is the equivalent number of free calcium molecules in the system? To solve this equation, to solve this for the free calcium, requires us that we solve for the value of this equation. One way to do this is essentially to subtract total calcium from both sides. So we have something equals to 0 on this left hand side and something else on the right hand side. So we must find the value of free calcium that makes this equation equal to 0. In other words, this is what's called finding the roots of this equation. Now we're all familiar with this, and I think the most simple example that we have all faced is in solving for the roots of a quadratic equation. So here we have the formula of a quadratic equation, right? And when a is positive, this parabola is facing up, like we have here, and we know what the formula for the roots are, which by now we have all memorized. The minus b plus or minus square root of b squared minus ac over 2a, right? This is a famous formula that gives you the roots of this equation, which again are the coordinates in the x-axis here, in the independent variable, at which this function crosses 0, right? Now for a quadratic function, we have this famous formula. It's very convenient and it's very useful. But for anything else, we don't have it, right? For example, in this case here, we don't really know what the right calcium level would be that would give you this root to be 0, right? So we don't have, for anything other than quadratic and linear equations and quadratic equations, we can have the values of the roots, but for anything else, of fourth order polynomial, for example, or trigonometric function, it's even more complicated. So what do? We're going to start with a particular guess. We call that guess, some value of x. So we call this x. X1 might be our first guess. And we're going to use the values of the functions as well as derivatives in some cases to update this x1 guess to something we call x2 that is a little bit better. It's a little bit closer to the root. And then we repeat the process. We update it to some x3, x4, xi, and so on, until we get to some value of the function that is sufficiently close to 0 for our purposes. So in this video, we're going to actually talk about two ways of doing this, finding roots of equations. One is so-called closed methods or bracketing methods, where we start with the knowledge that we have a leftmost point and or lower point and upper point. So here in this case, this is point 0 and point 1. And we know that in the left point and the right point, the value of the function are different. In this case, the left point, the value of the function is negative. In the right point, the value of the function is positive. So we start with that knowledge that the function has, the root of the function has been bracketed within the left coordinate or the lower coordinate and the rightmost coordinate or the upper coordinate. And what we're going to do is then we split the interval in half and check is the root to the left, to the right, and we repeat this process, right? So this is, for example, the bisection method that we'll cover in a second. Another category of methods have to do with so-called open methods. And Newton's method is one of these open methods, where here you essentially start with a guess. Here's our x1, and rather than try to find the root of this complicated equation, we approximate the equation locally, in this case with a line, and then we find where the line crosses 0, and we repeat this process. So here we don't, well, our initial setup doesn't require us to know 2 points, the leftmost and the rightmost, for example. Rather, this is an open method. There are pros and cons to both methods, which we'll cover. So let's look at the very basic method called the closed method, the bracketing method called the bisection method. And once again, we start with the lower xl and the upper xu guesses for bracketing the interval, right? And then we estimate the root to be right in the middle of these 2 points, right? So if we take the x lower, the x upper, and divide by 2, we end up with an estimate of the root right here. And then we check the root could be in this interval between the lower x and the root, the estimate of the root, or it could be between this interval here, which is the root, and the x upper. How are we going to determine where the root will be? Well, we'll check, and assuming that our initial bracketing step was right, we check where is the interval where the limits change sign. If they change sign and the function is continuous, that means the root must be in that interval, right? So one way to check whether some function changes sign in an interval is just to multiply the values of the function. And one of these have to be negative and one have to be positive for this to change sign. So this this multiplication has to be lower than 0, right? So we take, if the lower and the root is less than 0, then the root lies in this lower interval, in this part. And then so we restart the method now with x lower will be the same one and x upper will be this new root, and we repeat. We split it in half again, and on we go. If this is not less than 0, then the root must be on the other side. So we restart the method with the values of the other side. Of course, if this is 0, then that means that the f evaluated that the root is the real root, so you can stop. So this, if we don't do anything, right, most of the time you're not going to estimate exactly the function, the root of the function. You get close, you might get close, but not exactly. So in theory, the method will never stop. So we have to insert in our program something we call the stopping criterion that we can use to not let the for loop or the while loop, however we're implementing this, run forever. And one way is we check to see how the size of the interval, right? We know the root must be between uh, the leftmost part and the rightmost part, right? So the size of the interval keeps you divide by 2 at each iteration. So the size of the interval must decrease by a factor 1 over 2 to the n, right, from the initial size. One way to approximate this error, we can compute the approximate relative percentage error by being essentially the new root in the denominator, and in the numerator we have the new root minus the old root, right? And we multiply by 100 if we want a percentage, right? So this is telling us what's the difference between the new iteration and the old iteration divided by the new iteration, which is assumed to be a more correct, right? So and roughly speaking, this error decreases as a function of the iterations. The n here means iterations, and the error decreases as a factor of 1 over 2 to the n. So here's an example. So we have here a function, which is a nonlinear function. It's not a quadratic function either. So we don't have a formula to determine the root of this function exactly, right? Which is, again, the value of x such that f of x is 0. That's what's called the root. So we're going to use the bisection method. And here we're starting with the lower and the upper to be 0 and 1, right? So we split in the middle, and we get 0.5. And our initial approximate error is not available because we need 2 iterations to compute that, right? Because from formula above. So we check the left and the 0.5. Does it change sign in there? And the answer is no. So the root must be in this other interval. So we reset the x lower to be 0.5 now and x upper to be 1, and we compute the middle of that interval, which is 0.5. And we ask the question again, is the root between 0.5 and 0.75? It says yes, so we keep 0.5 and 0.75 as our new bracketing interval, and we repeat this, right? And you can see that the relative percentage error here is decreasing, albeit a little bit slowly, right? By the 5th iteration, we have an estimated error of roughly 5%. Right? And of course, we can keep going with these iterations for as much as we would like, essentially, or as much as we have time in the computer to solve and get the errors to as small as percentage as we would like in this case. So the only way that the bisection method can diverge, meaning it's in the sense that it's not going to converge to the root no matter how many iterations you take, is if your initial bracketing, your initial guess for the x lower and the x upper turns out to be wrong. In this example here up top, you have an example where the initial bracketing is wrong, meaning it's the f evaluated the x lower and f evaluated the x upper. That doesn't change sign, so you know there's a problem and there is no root in between that. So it doesn't matter how many iterations you choose here. In fact, bisection method will iterate to, it's essentially not going to work out. Likewise, you can have here a different setup where you can have the bracketing be between multiple roots, right? And in this case, depending on what the roots are, also your iteration can get stuck. The criteria that you check may not work out. So in these cases, which essentially summarized by the cases where the bracketing, the initial estimate of the lower and the upper x are incorrect, then the bisection method may not work out. So here are the summary points of what we've been talking so far. We've been talking about these bracketing or closed methods for finding roots of equation. Again, these are iterative methods. We start with an interval where we're confident that the function changes sign. In other words, there is a root in the middle. The bisection, as you see, if you start with the correct bracketing, it will converge, but it's rather slow converges. So next we're going to look at so-called open methods that can converge a lot faster, but they don't really have much of a guarantee that they will converge. It depends on where you start. So let's take a look. The starting point here will be what we call the Taylor series, right? So if we start with the Taylor series here, this is our old Taylor series that we've learned from calculus, right? F of x plus h equals f of x plus h times f prime plus h squared divided by 2 to f second derivative, and so on. You have a third order term on h and fourth order term on h and so on. But then we say, okay, let me stop here and let me truncate this series. So I will assume that my function, right, at a small step h away from x is given by this linear equation, right? And we'll start with some particular value x1, and then we're going to solve for what is the step h that this new approximated truncated version of my function is 0. Well, this is just the equation of a line on h, right? So I can solve for where this is equal to 0, right? So first I'll make the substitution that xi plus 1 will be this xi plus h. So this part here, x plus h, becomes xi plus 1, and f of x becomes f of xi, right? And the h here is essentially xi plus 1 minus xi, so this becomes our h, and here this f prime xi should have been of xi here as well, so there's a typo here. And then we solve for where this is 0, right? So we set, we would like xi plus 1 to be 0, so we set 0 here, and we figure out what the xi plus 1 is here, right? So all we have to do is move this guy to this side, divide by f of xi, f prime of xi, again this is a typo, should have been f prime of xi, and this gives us an update. And the error, as one can figure out from this Taylor series here, will be roughly proportional. So the error at the next iteration will be the square of the error of the previous iteration. So if we're in a situation where the error was small, let's say less than 1 before, the next iteration the error will be even less. And the stopping criteria here, of course, we're searching for the root because we don't know what the roots are, so we almost never really know the true value of the root. So this equation here on the bottom, which is essentially the relative error estimate, is not appropriate, right? It's not it's not a practical one, because we don't really know the true error. So oftentimes we approximate this relative error by subtracting the old estimate from our new estimate, assuming that the new estimate is better than the old one, and when this is converging, when this is indeed true, the next error will be the square, roughly speaking, proportional to the square of the previous error, right? Which for small errors it keeps getting better and better. So for example, if our previous error was 0.1, the next one will be 0.1 squared, which is 0.01. So let's look at this again. So let's say at the same example where we had before, let's say we want to find the root of this particular function, which is the same one where we use the bisection method. We start with with uh, with xi to be 0, right? So we start on this thing. We approximate this function with a line here, right? So this is the the Newton method, and we search for where this line crosses 0, so it will be roughly at 0.5 here, or exactly at 0.5, right? So if we fit a line according to the tangent here and ask where this line crosses 0, it will be at 0.5, and that's an improvement, right? Because the root here is close to 0.5, so we started right here at 0, so now we're at 0.5, and we repeat. So we evaluate the function at 0.5, it's not quite 0, but we fit the same line again through the Taylor series, and we get the next value, which is 0.56, and we're getting closer and closer, right? So by the fourth time, by the fourth iteration that where we repeat this, our error here is going to be something close to the 10 to the negative 8, right? Which is, and this approximation for the root got to be closer to the real root much faster than the bisection method, right? So these Newton methods can be really helpful when we have a starting point that is we know is safely enough, it's close enough to the actual solution. However, these methods can be a little bit unstable in that if you don't start the initial iteration with close enough to the root, the method can easily diverge, right? So an extreme point case here is this equation here on the right. So for example, let's say we start with our x0 here, our initial guess is exactly at this point. Here we have a flat Taylor series, right? The derivative here is 0. So this line here will actually never cross 0. So the method won't even work for even one iteration here. This is a really bad case. Here's a case that is also pretty bad, right? Here is a real root, but let's say if we start here, then we fit the line, and our first guess here would be that the root went even farther from the true root from the initial guess, right? So here's our x1, we repeat this, we get the new line, we get x2, and we keep doing this, and in this case this will be asymptotic but never really touch 0, so we get worse and worse. So the method doesn't converge, in fact it diverges. Another behavior that you can have from Newton's method is that it can just circle around the same points, right? So here you have an example where, for example, you start here at x equals 0, you get the line from the Taylor series, and you ask where this line crosses 0, and it's at this point, and you repeat, you get the other line, you go back, right? So you can cycle through this and never really get closer and closer to the real root here, right? So we really need a really good guess for our initial value, and of course it's a good idea to put a limit on the number of iterations so that this doesn't diverge. Plot your function, right? You may want to plot the function to see whether you're close to the root or not. These are all tricks that can be used to double check and verify that indeed you are getting better and better with respect to the approximation. Final method that I'll mention is that so far we have been using the actual Taylor series to derive an approximation for this line, right? You don't have to use the Taylor series. You can actually use two iterations to estimate the line, right? So your derivative f prime here, instead of being the actual derivative of the function, in some cases it may be hard to compute, or maybe you don't have it. You can subtract the past value of the function from the current value of the function, divide by the x positions, and you can, instead of getting the real Taylor series line, you get an approximate line, and you can solve for the root in something like an approximate Newton's method, right? So the convergence of this method is a little bit slower, It can also diverge in the same way that the original Newton method can. Um, but the benefit here is that you don't really need a formula for f prime in this case. So to summarize the contents of this video, the key points are that we talked about two types of methods for figuring out roots of equations, the so-called closed or bracketing methods and the open methods. The bracketing methods, they are safer as so long as you start with the correct bracket, but they take a lot longer to converge. The open methods can converge much faster because they use actually more information about the function. They use an estimate of the derivative or of the function, but they converge much faster, but they're much less safe. They can diverge. They can just essentially not work at all.